Hello, let's go over a bunch of Lagrange multiplier questions. These are all the questions back through 2016, and interestingly with this topic, it is very, very uncommon to see a pure Lagrange multiplier question on the final. In fact, out of the past six, we've only had one Lagrange multiplier question show up directly. So that's something to keep in mind as you're reviewing, but let's get started with this first question. We know that with Lagrange multipliers, we are going to need to find fx, fy, and sometimes fz, and we are setting those equal to gx lambda, gy lambda, that's it, yep, again, gotta turn my Wi-Fi off, and gz lambda, where these are our partial derivatives of our function f that we're trying to maximize or minimize, and these guys over here are gx, gy's, and gz's are the partial derivatives of our constraint function over here, which we call g. And then lambda, as we know, is just some constant that helps us solve these things by making our two, something like making our two gradients parallel to each other. Someone said that at some point, and I've been repeating it ever since. So could be telling you lies. So let's find these things. Fx is just going to be 3, and that's equal to 2x lambda. Fy is 2, that's equal to 2y lambda, and Fz is 6, and that's equal to 2z lambda. And let's see what we can do with this. We can say lambda is 3 over 2x. We can say lambda is 1 over y. And we can say that lambda is 3 over z. Now, from these, we can get some relations that will allow us to replace everything in our constraint with only one variable so we can solve. So let's start setting these things equal to each other. 3 over 2x is equal to 3 over z because they're both equal to lambda, and 1 over y is equal to 3 over z. So let's solve these in terms of in terms of z. Up here we'll get 3z is equal to 6x, or just z is 2x. And over here we will get z is 3y. And in fact, what we'd really like to have is these things in terms of the variable we're going to be replacing. So let's set that up like that. So now we can head back up to our constraint. For every x, we're going to replace it with a z over 2, so we will get z squared over 4 plus, for every y, we're replacing it with z over 3, so y, nope, not y, z squared over 9, and then we're adding our z squared, and all of that is equal to 4. Let's not deal with any of these fractions and multiply everything out. So if we multiply everything, well, let's put everything in terms of 36ths. That might help. So this will be 9z squared over 36. Here we'll get 4z squared over 36, and we'll get 36z squared over 36. And I don't know, 4 times 36, that's 34. 30, oh my God, 36 times 4 is going to be oh, okay, yeah, 144. It would be, wouldn't it? So 144 over 36, and this gets a little tedious. We'll make a little bit more space over here. In total, on our left side, we are going to get 36 plus 4 plus 9, so 49 over 36 z squared is 144 over 36. Multiply both sides by 36, divide by 49 and take a square root, and we will get z is equal to 12 over 7. And now the nice thing is, over here, we have a nice relation set up. We know that z over 2 is equal to x. So x is going to be 6 over 7. And we know that z over 3 is going to be y. So 12 over 7 divided by 3 is going to be y equals 4 over 7. And so now we can take what we know here and figure out our maxes and mins. And one important thing to note is that whenever we're, at least it works for all of these cases that we've had in these practice problems, well, old exam problems, whenever we have a constraint that's made up of squares, we have to note that in one of these steps back here, really here when we're solving, z is actually equal to plus or minus 12 over 7 and all of these as well. So we have to keep that in mind because that will, if we just solve it for positive, we will get our max and not our min. So, but it's good to know we only have to plug these things in once because our answer will be equal and opposite for our min. So plugging these in, 3x is going to be 18 over 7. 2y is going to be 8 over 7. And 6z, well, 6 times 12 is 72 over 7. And let's figure out what that is. 72 plus 18 plus 8, that's going to be 6, 7, 8. 98 over 7. And let's see, 7, 98, 1, 28, okay, 14. And so we see we're getting a maximum value of 14, and we know that our minimum should be equal and opposite, and so our answer choice is B. Let's find the minimum value of this thing. And a lot of these questions past that first one will be a lot easier. That's one of the more tedious ones. So, and I'm not going to go through the whole writing out fx, fy, lambda, gx, gy, all that kind of thing. And we're just going to do it like you would do it in your head for an exam problem. So we'll see that 2 is equal to 4x plus 5y, all multiplied by lambda, and 3 is equal to 5x plus 8y, that's terrible parentheses, all multiplied by lambda. And so we can say that lambda is equal to 2 over 4x plus 5y, and that lambda is equal to 3 over 5x plus 8y. So we can equate these two, and we'll see that 10x plus 16y is equal to 12x plus 15y. And that will give us y equals 2x when we simplify and combine all our like terms. So now with y equals 2x, we know that we need to plug this into our constraint function up here. And when we do that, every y we're replacing with a 2x. So we have 2x squared plus 10x squared plus, let's see, 4 times 4, so 16. X squared is equal to 28. And this works out to 28. X squared is equal to 28. So x is equal to plus or minus 1. And since we know that y is 2 times x, y is plus or minus 2. And that's great because we know that this thing up here, if we just take a look at it, it's going to be minimized when both of these are negative. So let's see, negative 2 minus 6 plus 2 is just going to give us negative 6. Let's find the maximum value of this big monstrosity. So in this case, we kind of do need some organization. Fx is going to be 4, x minus 2, y minus 1 squared. Fy is going to be 4, x minus 2 squared, y minus 1. And these guys are equal to 4x minus 2 lambda and 2. Oh, where'd I get that 4 from? I don't know. It's supposed to be a 2. And 2y minus 1 lambda. Okay, So it's not actually as bad as it looks, because we see if we divide both of these guys over, we can set these things up as 2y minus 1 squared equals lambda, and 2x minus 2 squared is equal to lambda. And that's great, because now we can set these guys equal to each other, and we see that y minus 1 squared is equal to x minus 2 squared. We can take square roots of everything. We get y minus 1 is x minus 2, which is the same thing as y equals x minus 1. And we can use this. We can plug it back into our constraint function up here. I'm gonna get some extra room. You can plug it into our constraint function up here, so we'll see that x minus 2 squared plus, well, this y is getting replaced with an x minus 1, so x minus 2 squared is equal to 2. Whoops, is equal to, oh my god, 2. And we can combine this up here to 2 quantity x minus 2 squared. We can divide that 2 out, get it equal to 1. We can take a square root, and we can, oh my god, my organization is terrible. This is equal to 1. We can add our 2 over and see that this is, when we're maximized, this is equal to 3. And if x is equal to 3 and y is equal to x minus 1, y is going to be equal to 2. And now we can just plug this in. So if x is equal to 3, f of xy is going to be 2 times 3 minus 2, so 1 squared, multiplied by 2 minus 1, so 1 squared, and that gives us 2. Let's find the maximum value of this guy subject to this constraint. And I don't know why they put this little blurb in here. It's usually unnecessary, but let's solve this. This should be one of the easier ones. We'll find that 2 is equal to 2x lambda, that 1 is equal to, 1 is equal to lambda, and that 4 is equal to 2z lambda. Okay, so this thing in the middle is kind of a godsend, because we'll see that over here, this is the same thing as lambda equals 1 over x. We still have lambda equals 1, and we have lambda equals 2 over z. Now, because we know that lambda equals 1, we can solve for x here and see that x equals 1. And we can solve directly for z over here and see that z equals 2. And all we have left to do is solve for y. We can do that up here. X squared is going to be 1 plus y plus z squared, which is 4. That's equal to 6. So y is equal to 1. And I'll put that up here too. Y is equal to 1. And there we go. So those are all of our positive answers. So it's looking like it's going to give us a good absolute maximum. And we can just plug these guys in here. We're going to get 2 plus 1 plus 8, which will be 11. And we're done. Okay, if the Lagrange multiplier method is used to determine the extreme values of f of x and y subject to that constraint, what are the Lagrange multipliers? Lambda 1 and lambda 2. This is the only time they've ever asked this kind of question where we're actually told to find the Lagrange to find the, I guess they're calling them the Lagrange multipliers. I just think of them as lambda, the lambdas, but I guess that's technically correct. So let's go through it. Although I'm pretty sure we shouldn't expect something like this. It's very uncommon. And as you've seen, I like to go through these questions without ever even figuring out what what our Lagrange multipliers are, which is actually fine. So we will see that 4 is equal to 4x lambda, and those both look like x's, 4x lambda, that negative 1 is equal to 2y lambda, and we have no z's, so we are good. This is, we can rearrange this to lambda equals 1 over x, and lambda is negative 1 over 2y. We can equate these, and we will see that 2y is negative x, and that's the exact kind of nice and simple thing that we want to get out of this, that we can then plug into our constraint. So for every well, let's flip this. Let's put the negative over here. For every x, we'll replace it with a negative 2y. So that will give us 8y squared plus y squared equals 1, or 9y squared equals 1, or y squared is 1/9, or y is plus or minus 1/3. And since we know that y is plus or minus 1/3 and that lambda is negative 1 over 2y, we can figure this out. So if we plug in 1/3 over here, we're going to get lambda is negative 1 over 2 times 1/3, which is 2/3. And we can rationalize this by flipping it, and we will get negative 3/2. And we would already be done because we see that answer choice B does it, but let's plug in negative 1/2 to make sure. If we plug in negative 1/2, all that's going to do is flip this sign, which is going to give us our 3/2, and we're done. Let's find our maximum m and our minimum m. I like in my head I always say them. I always say the capitalized one louder. I don't know if that's just a me thing. Let's solve this question. So we see that 2 is going to be equal to 2x lambda, and that 6 is equal to 2y lambda, and therefore 1 over x is lambda, and 3 over y is lambda. And as a result, y is equal to 3x, which we can plug back into our constraint over here, replacing every y with a 3x, and we will get 10x squared is equal to 10, or x is equal to plus or minus 1. And since we know this, y is equal to plus or minus 3. And yet again, because our constraint is made up of squares, we know that we're going to be getting equal and opposite answers, because when we plug 1 and 3 in here, we will get 2 plus 18. And when we plug negative 1 and negative 3 in, we will get negative 20. So, sorry, I should have been more clear. Negative 2 minus 18 is negative 20. And there's our answer. Okay, 2 questions left. This is a weirder one. It's kind of a Lagrange multiplier question in disguise. We know that the distance function is the square root of x minus x naught squared plus y minus y naught squared plus z minus z naught squared. And the cool thing about this is that about Lagrange multipliers, or just finding these mins and maxes in general, is that we can minimize or maximize the distance squared function and take a square root at the end. And this will all be much easier. Also, it's good to note x naught, y naught, and z naught are already given. Those are just, that's just the point that we're trying to figure out our distance from. So really, our distance squared function is x minus 1 squared plus y minus 1 squared plus z squared. And then we know that, and this is really, not g. That's exactly what it's not. This is our f. That's the function that we're trying to maximize. Well, in this case, minimize. We're looking for our shortest distance. And our g is our plane x plus y plus z is equal to 1. This is going to give us very nice and easy lambdas to deal with. In fact, it's just going to give us 1 lambda every time. And we'll see that. So 2x minus 1 is equal to, well, gx is just 1, so lambda. Same thing for y. 2y minus 1 is equal to lambda. And 2z is equal to lambda. So let's do what we did earlier. Since we're in 3 dimensions, we have to make some more complicated relations than we're used to in these 2D examples, but it'll be okay. We get 2. Whoops. 2x minus 2 is equal to 2y minus 2, and we can solve this to see that x is equal to y. So that's good. We like it when things work out that way. 2y minus 2 is equal to 2z. So we can say that y is equal to 2, whoops, y is equal to z plus 1. Okay, so these relations should let us do something nice with our constraint function over here. And in fact, they do. We can replace this x up here with a y. We can add a y, keeping that the same. And then we need to express z in terms of y. Well, z is just going to be y minus 1 plus y minus 1 is equal to 1. So we see that 3y is equal to 2, or y is equal to 2/3. And since we know that x is equal to y, x is also equal to 2/3. And since we know that y minus 1 is equal to z, z is equal to negative 1/3. Now all we have to do is figure out what our distance squared function is equal to, and then take the square root of that. So we're taking a big square root of x minus x naught squared. So that's going to be 2/3 minus 1 squared, so negative 1/3 squared, so just 1/9. The same thing goes for y. We're going to get 1 minus our, sorry, no, I had that backwards. For y, we're getting 2/3 that we have over here minus our y naught, which is 1, which will give us negative 1/3 all squared, which is another 1/9. And then for z we have negative 1/3 squared. So that's another 1/9. So overall, we're going to get the square root of 3 over 9, which is just root 3 over 3. And it seems like we've saved the easiest for last. Bet we can do this one in like 30 seconds. 2 is equal to 2x lambda. We know that that's going to give us 1 over x equals lambda. And then 1 equals 2y lambda. That's going to give us 1 over 2y equals lambda. We can, that's an x. Both of these are x's. That looks terrible. Lambda, lambda. So we know that 2y is equal to x. And we can use that. We can go put it up in the constraint. We'll get 5y squared is equal to 10, or y is equal to plus or minus root 2. And x is equal to plus or minus 2 root 2. We can plug that into 2x plus y, and we will get, we're looking for a maximum, so let's use the positive values. We will get 5 root 2, and we're done. Okay, that was kind of fun for me, but my standards are pretty low these days. So hopefully this was interesting, but spoiler, it's really not. This is just, a subject that they kind of throw in here, and you just have to go through the motions. There isn't, I was going to say the only fun thing about this topic, but then I kind of remembered there really aren't any fun things about this topic. I don't really like Lagrange multipliers. Give me a snow cone to integrate any day. Okay, but hopefully this was helpful if you needed the review.